Welcome to a new lecture, everyone. In this lecture, we will look at how we can visualize linear relationships. Now, a lot of data sets would have multiple quantitative variables, and the goal of our analysis is often to relate those variables to each other. Now, of course, we saw earlier how we can use the joint distribution of two variables, but it can be very helpful to use a statistical model that will help us estimate a simple relationship between what we call two noisy sets of observations. So we're using the common framework of linear regression for this particular lecture. Now, please understand that regression plots in Seaborn are primarily intended just as a visual guide that helps to emphasize patterns in a data set, especially when you're doing exploratory analysis. But do not consider Seaborn as a statistical analysis package, not at all. If you want to use proper quantitative measures that fit into regression models, you can use the stats model, right? So this is the proper package. The objective of using Seaborn is to make a dataset visually appealing and easy to understand for the user. All right, so we will import NumPy as NP. Then we will import Seaborn as SNS and import matplotlib.pyplot as PLT. We will also choose our tips dataset. So sns.load dataset tips. So there are two main functions that we use. We use the regplot and we will use the lmplot. Now both of these are very closely related to each other and a lot of the core functionality would remain the same. But it is important to understand how they differ as well. So let's do our first example. sns.regplot x is equal to total bill, y is equal to the tip, and data is equal to tips. Okay, I'm not sure why it is giving us an error. Just hold on. Oh, I forgot to double quote here. Right, so you can see a simple plot coming like this. You can also use an LM plot, and the difference would be not a lot, just a little bit, like this. So you should note that the resulting plots, while they are identical, the figure shapes are different. So you have to understand that the reg plot will accept the x and the y variables in a variety of formats, which include, NumPy arrays, Panda series, or any reference to a Panda data frame. In contrast, the LM plot has the data as a required parameter, which means the x and y variables must be specified as a string, right? So this is what we call as the tidy data set. So other than this input flexibility, everything else more or less remains the same. Let's do one more example. Here we want to see how we can fit a linear regression when one of the variables takes a discrete value. So sns.lmplot x is equal to the size and y is equal to the tip, and finally data is equal to the tips as well, right? And this is how the result would appear. So if you want to add a jitter, remember earlier I showed you how you can hide a jitter, but if you want to add a jitter, we can do that also. So here we will simply have to say that x jitter is equal to, let's say, 0.05. And the result appears like this. Another option is to collapse all the observations in a discrete bin plot to estimate the central tendency along the CI, the confidence interval, right? So what we're doing is we are collapsing all the observations in each discrete bin, which will help us plot an estimate of the central tendency along the confidence interval. To do this, lm plot, x is size, y is the tip, data is tips, and we will keep x, the estimator, as the mean. And the result appears like this. Now, all of the examples I have given you are simple linear regression models, which are very simple to fit, but this might not be appropriate for certain kinds of data sets. So we have a few examples where the simple linear regression provides an identical estimate of a relationship where a simple visual inspection clearly shows differences. So we'll take an example. So we have an Anscombe quartet. If you want to Google it, please do. So we'll say that Anscombe is equal to sns.load dataset, and we have Anscombe sns.plot. Sorry, we want to do an lm plot. X is equal to x, y is equal to y, data is equal to Anscombe, and we want to query this, and the data set is equal to I. We also have to make sure to put this inside a double quote, a single quote like this. Once we've done this, then we can say that the CI is equal to, okay, hold on, there's something wrong with my indentation. Let me just double check. X is x, y is equal to y. My data is equal to Anscombe dot query. We are, okay, we don't want to close this here. Perfect. And now we have the confidence interval is none. The scatter is equal to S, and let's keep it at 80. And it results in an error because I haven't closed the parentheses, and you can see the result like this. Now, the linear relationship in the data set is the same, but the plot clearly shows that it is not a good model, right? So what I want to do here is I want to take the same thing and put it below this, and we'll make this 2 and 1 moment. Okay, I think the S got left out. All right, so you can see this. Now, in the presence of these kind of higher order relationships, you can use the lmplot and regplot as a polynomial regression to explore simple kinds of non-linear trends. Right now, we are expecting a linear trend, but if you want to create a non-linear trend, you can do that as well. So SNS dot, in fact, I'll just copy the same thing. And here we only want to change one thing, which would be the order, that is equal to 2. Everything else remains the same. When we run this, we get a polynomial curve like this. And that is why we chose the order as 2. Now, there is another problem that comes which is due to outliers. So if I run this with, let's remove the order for now. We don't want a polynomial, we want a simple linear regression, and I'm doing it with the next data set. You would notice that there is an outlier in our data, which is this one in the top right column. Now, during this, there is a problem because you know that one data point doesn't fit very well, so the line is also not really accurate. So if you want to fit it into a robust regression, you can do something about it, which means you can do the same thing, but here we will say before our confidence interval, I will write that robust is equal to true. So what it does is it uses a different loss function to downweigh a relatively large residue. So I'll just write it here. So it uses a different loss function to downweigh relatively large residues. Like we had an outlier here, and when you run this, you will see the difference. Now you'll get a more robust line like this. Now when the y variable is binary, a simple linear regression also works, but the predictions are implausible. They don't really make any sense. I'll give you an example. So let's say we are looking at big tip, and my big tips are tips.tip divided by my tips dot total bill, which is greater than, let's say, 0.15, and sns dot lmplot x is equal to total bill, y is equal to big tip, and we have data is equal to tips. We will also say that y jitter is equal to point, let's say 0.3. So you notice that it works, the linear regression works, but it is implausible, right? It doesn't really make much sense. Now, what's the solution here? When you want to use a linear regression, but you want to do it with a binary data set, you want to use a logistic regression. So we'll use a logistic regression here. And this means that the regression line shows the estimated probability of y is equal to 1. So this is the estimated probability for a given value of x. Let's see how we do this. So we can just copy the same thing, and the difference would be that we don't want the, in fact we want the jitter. Let's keep the jitter as well. We will say logistic is equal to true, and this time you notice we get a logistic curve like this. Now again, like I had mentioned earlier, remember this is computationally very intensive. By the way, this is also true for the robust regression. So compared to the simple regression, these will be computationally more intensive. That means that if the dataset is very large, it might take some time. If you want to use something which is computationally intensive, but it also has the confidence intervals not computed. So let me explain that. Let's do one more example. So like I said, this is computationally very intensive, right? And The same holds true for your robust regression as well, right? Now, the reason this happens is because the CI, or the confidence interval, around the regression line is actually computed using a bootstrap, right? Now, one option is to simply turn the CI off. So we can say CI is equal to none, and that will work. Now, there is a different method here for a non-parametric regression, and this is called the lowest smoother. Again, you can Google this. Now, this has the fewest number of assumptions. Now, do remember that this is also computationally intensive, and so the current confidence interval are not computed at all. Let's take an example. So sns.lmplot, in fact, let me copy this. And we want to remove the jitter and the logistic, and we will say that lowest is equal to true, right? And let's not keep big tip, let's just see the tip, and the result would look like this. All right. Next, we want to do the recit plot. For this, we will create a data set, or rather use the same data set. We will copy this line of code, and we will say x is equal to x, and then y is equal to y. And we're using not the tips dataset, we'll go back to the Anscombe dataset. And like we did earlier, we will query, and we will only take the dataset equal to I. And we will say that, like we had done earlier, the scatter underscore KWS is equal to colon 80. Perfect. And there's an error here. Let's quickly see why this is coming. One moment. So we have, oh, we don't want to use the error plot. We've also used the recit plot, but we're still getting an error. Let's check. So we have data not dot equal to anscombe dot query. Perfect. And like this. So if the residues have a structure, it suggests that the linear regression, the simple linear regression, is not appropriate. For example, if I do the same thing with the second one, you will notice that it tells us that it is clearly not appropriate. Let us now see how we can condition on other variables. I'll call this conditioning. So all the plots that we have done before, they helped us explore the relationship between a pair of variables. But sometimes you might have a question on the lines of, how does the relationship between those two variables change as a function of a third variable? So relationship between two variables change as a function of another third variable. This is where the difference between a reg plot and an LM plot comes. So while a reg plot will always show a single relationship, the LM plot will combine the reg plot with the facet grid. So the LM plot combines the reg plot with the facet grid. And this allows us to give an easy interface where we can see additional categorical variables. Let's take an example. So first we will say sns.lmplot x is equal to total bill, y is equal to tip, And then we have the hue, something we haven't used earlier. So the hue would be the smoker, and the data is our tips data set. So you notice we get two different colors like this with two different lines. Now, in addition to the color, it is also possible for you to use different scatterplot marker to make the plot reproducible either on black or white, or to make it color accessible. To do this, I can copy the same thing, and this time we will select everything that we have right now. So total bill, tip, the hue is smoker, but in addition to this, I will also set my markers as two symbols. So I select a O and an X, and let's also choose a palette. So we can choose any palette we want. Let's say set 2. So we get different markers and different colors as well. So we have full control over both of these elements. If you want to add another variable, then you can draw multiple facets, which each level of the variable appearing in the rows or the columns. And this means we will keep the hue, and after that we will select the column which is equal to, let's say, the time. And this time you notice we get two separate charts. The first one shows us yes and no for lunch, and the second one shows us a yes and no for the dinner. Similarly, we can do this one more time, and this time we will also keep something in our row. So let's say the row is equal to maybe the time, and we get four charts now. So we are able to see column is time. I'm sorry, let me not choose this as the time. We have already chosen time. Let's choose this as the sex. And you notice we get four different visuals right now, one each for every combination of the time and the sex. If you want to control the size and shape, that is also possible. So we'll have to first create a figure object. So plt dot subplots, and my figure size is equal to, let's say, 5, and then we can say rect plot, where x is equal to the total bill, y is equal to the tip, and we have data is equal to tips, and ax is equal to ax. Right? So we can control the size like this. For example, if I make it 10, then the height will increase. Right? So let's try this the other way around. Let's make it 15 and 5. So we get a slightly wider chart now, like this. Now, remember, for the LM plot, you will have to use the facet grid using the height and the aspect parameters, right? Not directly on the figure. This means this will be sns.lm plot. X is equal to our total bill. Here we have y, which is equal to the tip. Column is equal to the t. Data is tips. And then we say the column wrap is equal to 2. And we say that the height is equal to, let's say, 4. Let me try that once again. Right, let me remove this. Okay, right. So we're able to get the result that we're not able to see. One moment, everybody. You know what? Let me just type it once again. So we have sns.lm plot. There we have We can copy some of these things at least. So X is total bill, Y is tip, data is tips, which is great. After that, we need to have our column is equal to the day. Then we have the column wrap, which is equal to 2, and the height is equal to 4. So we're able to see 2 columns and a height of 4. And obviously you can change it. So if you make it a column wrap of 4, then all the 4 will appear together like this. Let's also see how we can plot a regression in other context. Let's take an example. So we'll do a joint plot. X is our total bill. Y is the tip. And we have data is equal to tips. And we have the kind as REG, and our result will look like this. Let's do one more example. So this time we're going to use a pair plot. Now in this, we will combine the kind as REG, which will combine the reg plot and the pair grid, which will show us a linear relationship between variables in a data set, right? Now do remember, this is a little different from the LM plot. So what we're going to create, the two axes do not show the same relationship conditioned on two levels of a third variable. The idea here is that we want to use the pair grid to show multiple relationships between multiple pairings of variables in a data set. It will be clearer when I do the example. So we use tips X, and this is our total bill, and we have our size. Then we have Y, where we have the tip. Then we have a height of 5. We have an aspect of 0.8, and we have a kind as REG. So you notice that the two axes do not show the same relationship on a third variable. We are using it to show multiple relationships between multiple different pairings in a data set. So we have total bill, tip, and we have size and tip like this. We can also use a hue parameter here. So copy and paste it. And everything else will remain the same, but we will simply add the hue equal to the smoker. And this way, we get two different lines for each of these two visuals. That will give us the categorical variable. So that concludes our lecture.